So we've been learning different techniques of finding derivatives without having to use the formal definition. Well, we've been using the formal definition to help us prove and get these formulas. And so today we're going to be looking at the derivative of trigonometric functions. And the first one we're going to look at is the derivative of sine of x. And so in front of you, we have that derivative. So the derivative of sine function is the cosine function. So one way to write that is d dx of sine of x. So that's saying I'm going to take the derivative of sine of x. I'm getting back cosine of x. So there's a couple of different formulas that we need to recall in order to go through and prove this is true. And so two of them are from your trig course, the sum and difference of two angles or two real numbers. And we have sine of a plus b. This is equal to, how I remember this, sine of a plus or minus b is always sine, cosine, same sign, sine, cosine. Okay, so sine of the first angle, cosine of the second, plus sine of the first, cosine of the sine of the second, cosine of the first. If it was a cosine sum or difference of angles, it's always cosine, cosine, opposite sign that's in between, sine, sine. And that's just how I memorized those from the past. So we need to know those, and those are going to help us manipulate things to fall out nicely. And then we also need to remember when we take the limit as sine of h over h, as h approaches 0, this was equal to 1. Okay, so let's look at this proof and let's prove that the derivative of sine of x is equal to cosine of x. And so we're going to do that by looking at that formal definition of the derivative. And formal definition says that we're going to look at the limit. Whoops. We are going to look at the limit as h approaches 0 of sine of x plus h minus f of x, so sine of x, all over h. So let's use the sine of the sum of two angles or real numbers and rewrite that. And so sine of x plus h, that is sine of x cosine of h, same sign plus sine of the second angle h cosine of the first x. And then let's bring down the minus sine x all over this h. So how it's written right now, I want to rewrite the numerator. I want to rewrite the order so that I can group two terms together and pull out sine x. And so this is the trick in this one. And so to do that, I'm going to rewrite this as a limit as h goes to 0 of sine x cosine h minus sine x. And then I'm going to plus sine h cosine of x all over h. So all I did was I just reordered the terms, swapping the last and middle term in the numerator. And so now let's just group the first two terms together and let's factor out a sine of x. And so if we factor that out of the first two terms, so why don't you guys go ahead and do that while I move this down. We would have sine x all times that quantity cosine of h minus, pulling sine x out of sine x, we're just left with 1, plus sine of h cosine of x all over h. So since I haven't taken the limit yet, we want to make sure that we bring that down also when we rewrite this. Right now, if we plugged in 0, we're going to get that indeterminate form of 0 over 0. But we know by limit rules that we can break this down. So let's rewrite this as the limit. Rewrite this as two separate fractions. So we're going to look at the limit as h goes to 0 of sine x all times cosine of h minus 1 all over h, plus the limit as h goes to 0 of sine h all over h times cosine of x. And so we can do that because of limit rules. Sorry, things are jumping around. Okay, so notice that our limit we're taking is with h. H is approaching a value. So if we ever have a piece of the function where it doesn't have an h in it, and so notice that this sine x in here, right here, doesn't have an h in it, we can think of that times this function cosine of h minus 1 over h. Same kind of idea here. This cosine of x, that piece doesn't have an h in it. We can think of it as multiplication right here. So we can actually pull these pieces in front of our limit and have it as multiplication. So in this first term, we can say, well, this is the same thing as sine of x times the limit as h goes to 0 of this cosine of h minus 1 all over h. Plus, let's bring the cosine of x out front of the limit times the limit as h approaches 0 of sine of h all over h. And so now if we go in and we do our direct substitution, we're going to get 0 over 0 in each case. But recall one of those formulas I told you that we needed to remember was that the limit as h approaches 0 of sine of h over h equals 1. The other one, which I forgot to write in there, is this one right here. So limit as h goes to 0 of cosine of h minus 1 all over h. This is equal to 0. Okay, so we had shown that, I believe, in a previous course. And so we're going to just use that fact to find the direct substitution, what we would get when we look at those limit pieces. And so in front there, we have sine of x. And now taking that limit, we know that that limit as h goes to 0 of cosine of h minus 1 over h, that is equal to 0, plus cosine of x times the limit of sine h over h as h goes to 0. We had talked about that was the limit was 1. So anything times 0 is 0, plus cosine of x times 1 is just cosine of x. And recall, that's what we were looking at, was taking the derivative of sine of x. We got back cosine of x. So you just had to remember a couple of limit rules from the beginning of the semester and those couple of trig identities. and see the trick on how to manipulate it so it would fall out. But now that you've seen that trick, then it's pretty easy to show the same thing when we're looking at the derivative of cosine of x. Once we know the derivative of sine x and cosine x, when we find the derivative of the other trigonometric functions, we're just going to rewrite them in terms of sine x, cosine of x, and then use the difference quotient or difference rule. Derivative, sorry, we're gonna take the derivative using the quotient rule. There we go. Okay, so I'm going to give myself some more room, and we are going to look at the derivative of cosine of x. And I'm actually let's start by just finding it, and I'm not going to give it to you. So we're going to look at the derivative d dx of cosine of x. So derivative of cosine of x using the formal definition of a derivative is equal to the limit as h goes to 0, f of x plus h. So cosine of x plus h minus f of x. Well, f of x is cosine of x, so minus cosine of x all over h. So let's use our rule again for the sum of two things. For cosine, that's cosine, cosine. So cosine of x, cosine of h, opposite sign minus sine of x, sine of h. And then bringing down the minus cosine of x that we also had up in the numerator, all over h. So notice again, we can regroup this. And if we regroup it, swapping our middle and last term, we can factor out the cosine of x. So let's just go ahead and do that while we rewrite it and pull it out. So if we pulled out a cosine of x from this cosine of x, cosine of h, you're left with just cosine of h. Minus, if I pull out a cosine of x from cosine of x, I'm left with 1. And then rewriting that middle term, so bringing it down minus sine x, sine h, all over h. We haven't taken the limit, so we're going to just bring that down. Oops. Should have been sine x. So again, we can break this down as two separate fractions, and we can pull the pieces of that function that doesn't have an h in it in front of the limit. So using our rules, so we can rewrite this as cosine of x times the limit as h goes to 0. So I'm going to be left with this piece in here. So cosine of h minus 1 all over h. And then I technically really shouldn't have those brackets there, but I was just kind of showing you what we were pulling out. And then minus the other fraction. So breaking it down, this is each grouping in the numerator. So we have minus the limit of the second fraction. Oops, but I wanted to pull out the term sine of x, because it's really sine of x times that. That doesn't have an h in it, and we're looking at the limit as h goes to 0. So this would be sine h all over our denominator of h. Well, the limit as h goes to 0 of cosine of h minus 1, that all over h, that goes to 0. Minus sine x, and then the limit as h goes to 0 of sine h over h, that was 1. And so cosine of x times 0 is 0. And then we have minus sine of X times 1, which is negative sine of X. So we just saw or proved that the derivative of cosine of X is equal to negative sine of X. Once we find the derivative of our other trigonometric functions, you'll notice, and this is kind of going to be helpful to help you memorize so that you don't have to do this, is that when we're taking a derivative of some trigonometric function that has co in front of it, it's going to end up that that's going to give us back a negative when we take the derivative. So cosine has a co in front of it, cosecant, cotangent, those are all, when we take the derivative, you'll see we'll have a negative. If they don't have that co in there, like sine, secant, and tangent, those, when you take the derivative, we'll see are positive. Okay, so now we can use this fact, and you just kind of need to either memorize this, or you're going to have to quickly do it so that when you're on an exam that you know it, because you're not going to have those notes. So let me, before I move this, see if there's any questions on that work or what we're doing. Okay, so we had just said that if we were taking the derivative of sine of X, we found that that was equal to cosine of X. If we were thinking about this graphically, let's look at the graph of sine X real quick. So I tend to break it down into a period. So pi fourths, pi halves, pi, 3 pi halves, and 2 pi. Sine, I know at 0. So I want to graph what I'm first graphing is y equals sine of X. So I know that when I have 0, sine of 0 is 0. Sine of pi fourths, that's root 2 over 2. Sine of pi halves, that one is 1. Sine of pi, that gets me back down to 0. Sine of pi halves, that gives me down, oops, I missed one. I actually added an extra one that I normally don't do. I normally don't do that pi fourths. And I was thinking that it wasn't too symmetrical, so let me just rewrite that a little bit. Sure, let's do this. Okay. So 0, up to 1, back down to 0, down to -1, back up to 0. So this is our original function. So now let's talk about our derivative function. And so we had been talking about before graphing the derivative function. So let's look at our original function and notice that it is increasing. And we know that the derivative is talking about the slope. And so the graph is increasing here. From 0 to pi halves. And then it's also increasing here from 3 pi halves to 2 pi. So recall, if our graph is increasing our function, then we know that our derivative is going to be greater than 0. It's above the x-axis. And then if we look at when our graph is decreasing, so when this is the original function going downwards, what we know about this graph, it's decreasing our original function on the interval from pi halves to 3 pi halves. And so for my derivative function, if I have a derivative, that slope there, that's less than 0. So I know that my derivative function, this is going to be below the x-axis. So other thing that helps us to graph the derivative function is to find out where is that function have a max or a min, or where is that tangent line equal to 0. So the slope is equal to 0 when our tangent line is horizontal. And so our tangent line is horizontal at max and min values that aren't cusps or sharp corners, but those aren't differentiable. So, but these are differentiable. It's smooth and curved. It's continuous. And so this is when our slope is equal to 0 for our original function. Well, if our slope is equal to 0, then our derivative is equal to 0. And that's where it's going to be crossing the x-axis. So then f prime of x crosses the x-axis there. Okay, so let's now look at this with a graph of cosine of x, which we were just found that that is our derivative function. So let's graph f prime of x. And at the same time, let's kind of look at what we were looking at with our original function. So if we graph f prime of x, and we know that we said that was cosine of x, recall cosine of x, and maybe I should do it below, just so we have some more room. And that we're not getting confused between the two graphs. I'm going to break it up into 4 major points: pi halves, pi, 3 pi halves, and 2 pi. Well, cosine of 0 is 1. So it started up here. At pi halves, we get 0. At pi, we get -1. At 3 pi halves, we're back up to 0. And at 2 pi, we're back up to 1. Okay, so notice that first piece between 0 and pi halves, what did we say? We said that the derivative function, it was increasing, it had to be above the x-axis. So notice that this piece is above the x-axis between 0 and pi halves. Then we said that when our slope is 0, that's where it's crossing the x-axis. And so notice we have our slope 0 here for original function is crossing here at pi halves. We then said, okay, when our function is decreasing, then our original or our derivative function has to fall below the x-axis. And so notice that that whole piece is below the x-axis here. Again, we have slope is 0. That's where it's crossing for our derivative function. And then it's increasing, so it's above the x-axis. And so it kind of just fits. I'm not going to show it with derivative of cosine of x and the derivative function being negative sine of x. But the same thing would happen if you were to compare the two graphs and what you know about the derivative of a function and what's going on and graphing the derivative function. Okay, so let's look at some examples. Okay, so in front of you is the derivative of our other trigonometric functions. Derivative of tangent x is secant squared x. Derivative of secant x is secant x tan x. Derivative of cotangent x is negative cosecant squared x. And derivative of cosecant x is negative cosecant x cotangent x. I don't have these memorized. I'll memorize them again soon, but I can always quickly derive them if I need to. And so let's talk about it. I don't want to go through and show each one just because I want to get to some other examples. But this is something that could be on an exam where I ask you to derive by using the formal definition of a derivative, what the derivative of this trigonometric function is. So let's look at tangent of x. That's one that's used a lot. And so the derivative of a tangent of x, oops. Let's get rid of that. Just 1 second before we start. Okay, so we're looking at the limit as h is approaching 0 of tan of x. Actually, what am I doing? We don't have to do that. We're not going to do the formal definition. Let's do this. The derivative of tangent of x. This is the same thing, right, as saying the derivative. Let's rewrite tangent of x in terms of sine and cosine. So tangent of x is the same thing as sine of x over cosine of x. We've already derived the formulas for the derivative of sine and cosine. We need to use the quotient rule. So the quotient rule says we're going to first take the derivative of our numerator. And so the derivative, and I'm just going to write this out, that we're going to go do it, and not take the derivative yet. So derivative of our numerator, which is sine of x. We're supposed to take that all times our denominator, cosine of x, minus our numerator, which is sine x, all times the derivative of our denominator, so d dx of cosine of x, all divided by our denominator, cosine of x, quantity squared. Okay, so that's what the quotient rule says, and we just put it that we were going to go take the derivative of each of those pieces. So now that we're there, derivative of a sine x we said was cosine of x, all times cosine of x, minus sine x. We just saw that the derivative of cosine of x, that one is negative sine x.
It's frozen.
Okay. So, just stop it really quickly. Jump back in. And so sharing my screen again. We're just using the quotient rule. We just took the derivative of cosine of x and I just rewrote it down here as negative sine x. And now we're going to put that over cosine of x quantity squared, which recall we can write that as cosine squared of x. Okay, well, cosine of x times cosine of x, that's cosine squared x. but we can write it like this, cosine squared of x, minus sine of x times negative sine of x. So that's really plus sine squared x all over cosine squared x. So hopefully you recognize that trigonometric identity, that Pythagorean identity, cosine squared x plus sine squared x, recall that was 1. And so we have 1 over cosine squared x, which we can rewrite as same thing as 1 over cosine of x quantity squared, because 1 squared is 1. Now we write 1 over cosine of x in terms of its trigonometric function, and 1 over cosine is secant squared. So secant squared x. And so the derivative again of tangent x is secant squared x. So you would do that for all of the other trigonometric functions to find the derivative. You would rewrite it in either terms of sine or cosine or both, depending on the trigonometric function. And then you would have to use the quotient rule when you took the derivative. Let's just look at one. Let's look at maybe cosecant. Cotangent has both sine and cosine, but the other trig functions just have in terms of one trigonometric function. So the derivative of cosecant. Again, remember what I was telling you guys, that if the trigonometric function has the co in front of it, remember that one way to remember is this is negative co. One of the other things, the other ones, tangent of x and secant of x, notice that they both have secant in them. And you'll notice that the ones with co both have cosecant in them and cotangent. Okay, so those are just maybe tools to help you maybe memorize them. Okay, so we're taking the derivative of cosecant of x, but we can rewrite the derivative cosecant as 1 over sine of x. Now we can go through and we can use the quotient rule. So quotient rule says the derivative of my numerator, well, d dx of 1 of a constant, that's going to give me 0 times my denominator, sine of x, minus my numerator, so minus 1 times the derivative of my denominator, so d dx of sine x, all over my denominator quantity squared. So again, the derivative of a constant is 0. And so 0 times that sine x, that goes away. And we have -1 times the derivative of sine x. Sine doesn't have co in it, so it's going to be positive, and that's the other trig function cosine. So this one's going to be minus that 1 times cosine of x, so minus cosine of x, all over sine of x quantity squared. So let's rewrite this. Let's rewrite sine squared x as sine x times sine x. And so our numerator, we have minus cosine of x, all over sine x times sine x. So I can technically break this down as 2 separate fractions. I can write that down as negative cosine of x over sine x times 1 over sine x. And I see a lot of chats coming in, so let me pause the video and let me see what's going on. Okay, so we're almost there. Treat this as 2 separate fractions. And now think of this, because multiplication, we can do that. Negative cosine x over sine x. Well, cosine over sine, remember, is cotangent. And so this is going to be negative cotangent of x. All times, well, 1 over sine of x. This one is cosecant x. So the derivative of cosecant x, this is equal to negative cotangent x cosecant x. So I'm going to pull a couple examples from the end of the section for us to do. So let's look at how about f of x equals x times sine x times cosine x. Or how about actually x cubed times sine x times cosine x. And we want to find the derivative of f of x. Okay, so looking at this, I notice we actually have a product of 3 separate functions: x cubed, sine of x, and cosine of x. I want to break this down so I can use the product rule. I just notice I'm going to have to use this twice. And so it depends on how you want to break it down. I can group, depending how you want to group it. We can group the first 2 pieces together, x cubed and sine of x, and then multiply that times cosine of x. I can group cosine of x and sine x together. It depends on how you want to do it. I'm going to just group sine x and cosine of x together, just hoping that maybe, I don't know, something would turn out with some trig identities. And so I'm going to have to use this product rule. And within the product rule, I'm going to also have to use the product rule. So I'm going to write this down first without taking the derivative, so I don't miss anything. So I'm taking the derivative of my first function. So derivative of the first, x cubed, times my second function, and I wrote my second function as sine of x cosine of x. And then plus, that's the product rule, my first function, which is x cubed, times the derivative of the second piece, which I called sine x cosine of x. Okay, so the first one is pretty easy. Derivative of x cubed. Hopefully you guys have that general power rule down. Bring our power down front, subtract 1 from our exponent, we get 3x squared. All times the sine x cosine of x. Plus x cubed. But again, I need to use my product rule. And so derivative of the first, I'm going to just, I know it's kind of tedious, but I think at first it's best that we do this. So derivative of the first, derivative of sine of x, all times the second, cosine of x, plus the first, so that's sine x, times the derivative of the second. derivative of cosine of X. Okay, so that first grouping, we're all done. We have 3x squared sine x cosine x. Plus x cubed. So inside that bracket, derivative of sine x doesn't have the cos, so it's going to be positive. So this is cosine of x times cosine of x plus sine x, and then the derivative of cosine of x, it has a cos, so it's going to be negative. So that's negative sine of x. So we have 3x squared sine x cosine x plus x cubed. So cosine x times cosine x, that's cosine squared x. And then it's going to be minus sine squared x. I'm just seeing if there's anything in here that can help me factor it. So we're going to get to the point we're going to try to find where these derivatives are equal to 0. So it's really kind of important that you're able to simplify things down and then be able to factor things. In this case, or rewrite them using, in this, I don't know what we're doing, rewrite them using trigonometric identities, if that could help us. I noticed that there's an x cubed in common, so I could factor those x cubes out and then see if there was any way I could factor, because it's really a quadratic then. But for now, because we're running out of time, this class is so short, I want to look at one other problem that you're going to see in the homework. So I'm not going to do that piece right now, but we'll be, just forewarning you, we're going to be doing that soon. So other piece in your homework, finding the derivative of trigonometric functions. So if you need to use your product rule or quotient rule or rewrite your other trig functions in terms of sine or cosine to help you. The other piece is looking at limits. And so, for example, if you looked at the limit as, let's say, theta is approaching pi 6 of sine of theta minus 1/2 all over theta minus pi 6. So with all of these limits that are asking you to look at, always go through and do direct substitution. You'll find some of them will fall out and you get an answer right away. Some of them, like the one I just chose, you're going to get that indeterminate form 0 over 0. And so we're going to need to either try to manipulate it or see what this really is telling us to do. And so notice if we look at this and we plug in pi 6 wherever I see a theta, I see my denominator pi 6 minus pi 6 is 0. And I see my numerator sine of pi 6, which is 1/2, minus 1/2 is also 0. And so I, again, to get that indeterminate form. But we normally didn't look at the derivative in this form, but recall that the derivative of a function a, this is a limit as x is approaching a of f of x minus f of a all over x minus a. And so if you think of the derivative in that alternative form, notice that my function I can see is f of x. Well, in our case, f of theta would be sine theta. It doesn't have x in there. if we look at what is f of, and my a value in my case is pi 6. So if I look at f of pi 6, this is sine of pi 6. Does that give me back 1/2? And it does. So f of x minus f of pi 6 all over theta minus pi 6, but and a was pi 6.
Sorry, I froze again.
Oh no. So this is basically just the derivative of sine of x at pi 6. And so we can write this as sine of, or f, we're looking at the derivative of sine of pi 6. So hold on, let me restart this so I can show it writing. Okay. Zoom. Oops. For some reason, it's not working this time. So what I was just saying is that we want to find f prime of pi 6. And we're given what f of theta of it is. So if we wanted to find the derivative of sine of theta, so f prime of theta, that one is cosine theta. Now, if we evaluate this, plug in pi 6 wherever we see cosine, we get cosine of pi 6. And cosine of pi 6 is √3/2. So this limit that gave us an indeterminate form before, just recognizing that that was the derivative of sine theta, it was just the formal definition written that way, we can use that information. Take the derivative of that function, and we know the derivative of those trigonometric functions, and then plug in that value that we were approaching. Okay, so that is all of 3.5. So I would be happy if you guys want to go over more problems in student hours. I have other videos of teaching this section. So if you want to see more examples, I can post those on your Canvas page. But we are a little bit behind compared to, like I told you, the other instructor, but also where I've been in the previous semester, comparing the weeks that were in week 8 and where I was in week 8 in a different semester. So how much I love this section and the next section I'm going to teach tomorrow, I feel like I have to speed a little bit faster through it. So I apologize, but I'm here to help you in student hours again. And then tutors are here to help you.